these are probabilities that change based on conditions. One example of this would be playing the card game high-low. So high-low is a pretty easy card game to play. You shuffle a deck of cards, you flip over the top card, and let's say that you flip over, when you do this, let's say you flip over the 3 of spades. The game is, do you think the next card will be higher or lower than the 3 of spades? And you have to guess. What do you think? Now, there's probabilities involved here, right? In your brain, you're thinking, okay, the cards that are lower than the 3 are just the 2, and the cards that are higher than the 3 are 4 through ace. So there are a lot more cards that are higher than the 3 than are lower than the 3. So the probability that the next card is going to be higher is probably pretty good. So you would guess that the next card is probably going to be higher. And so you guess, you say, I think the next card is going to be higher. And so then the dealer flips over the next card, and lo and behold, it's a jack of diamonds. And you're like, yes, you were correct. Great. But you got to get 3 in a row. Okay. You got to get 3 in a row. So now you have a jack of diamonds. What's your guess now? And again, the probabilities change. When you look at the jack of diamonds, the cards that are higher than the jack of diamonds are the queen through the ace. So you got queen, king, and aces. The cards that are lower than the jack of diamonds are 2 through 10. So it's not quite as obvious as the 3 of spades, but you still have a significant amount of cards that are lower than this card than are higher. And so your guess is going to be, you probably think that the next one's going to be lower. And so you're going to guess, I think it's lower. Your response changed due to the conditions changing. When you had a 3 of spades, you guessed one way. When you had the jack of diamonds, you guessed another way. The conditions changed, and so your probabilities change. So you say, yeah, I think it's going to be lower. And so the dealer flips over the card, and look at this. You get the 8 of clubs. And now to win the prize, you have to guess higher or lower. So what do you guess? If you look at the 8 of clubs, the cards that are higher are going to be 9 through ace. So 9, 10, jack, queen, king, ace. So there are potentially 6 cards higher than the 8 of each suit. And if you think about the cards that are lower, it's going to be 2 through 7. So 2, 3, 4, 5, 6, 7. So again, there are 6 cards, one of each suit, that are lower than the 8. So what do you guess? Is it 50-50? How many cards have been dealt? Are you keeping track of the cards that have already been used up, right? Because the conditions change, the probabilities change, and your response to high or low also changes. This is an example of a conditional probability. So when we talk about conditional probabilities, we're going to write them this way. A is the event that you're trying to find the probability of, and B is the condition that you're going to apply to the sample space in order to reduce it down. And so let me kind of explain this another way. If you go onto Amazon and let's say you're looking for shoes, you could type in shoes and you would get a list of all different kinds of shoes, right? But then you apply the condition, the filter, that you're looking for blue shoes. So you click the button under color that says filter by color and you select blue, and now it shows you only the blue shoes. So you went from all the shoes, the entire sample space, down to a restricted sample space, the blue shoes, by applying the condition that you only wanted to see blue shoes. That's the same thing we're going to be doing here. So the green part is the condition that you're going to apply. So here we go. Let's take a look at this. Again, we're rolling 2 dice. And so this is our task. What is the probability of finding, rolling 2 dice and getting a sum of 5 given the first die is a 2? So the event that we're trying to solve for is the sum of 5. But we have to first apply the condition that the first die is a 2. So if we go and look at our sample space, this is the entire sample space. And there are 36 outcomes in this entire sample space, right? 6 by 6. Okay, there's 36 of these. But we have to first apply the condition that the first die needs to be a 2. So our sample space gets reduced. It becomes what's called a restricted sample space. So we no longer have all 36 items. We now reduce our sample space down to 6 outcomes. It's kind of like applying the filter to the shoes to say, okay, I see all the shoes, but I only want to look at the blue shoes. Once you have filtered to the blue shoes, now you calculate your probability. So now that we've reduced our sample space from 36 outcomes down to 6 outcomes, now we look at the event that we're trying to solve for, which is the sum is 5. So of these, only one item has the sum of 5, and this becomes our new event space. And so the probability is going to be 1 out of 6, not 1 out of 36, not the entire sample space. It's 1 out of 6. And so what you do is you apply a condition that reduces your sample space down to a restricted sample space. And then using that restricted sample space, you calculate the probability of your event only with that restricted sample space. So this is conditional probabilities. And so here is, we're going to draw a single card from a deck. What is the probability that you draw a spade given that the card is a jack? The event that we're looking for is that the card is a spade. That's the probability that we're trying to solve for. But we have to first apply the condition that the card must be a jack. So we take our sample space and we reduce it down to only the jacks. So this is now our restricted sample space. And now using only this restricted sample space, we find the probability that the card is a spade. And there is only one card right here that meets that condition. And so the probability is 1 out of 4, not 1 out of 52, not 4 out of 52, 1 out of 4. So you're taking your entire sample space, reducing it to a restricted sample space, and then calculating the probability of the event just with that restricted sample space. So why do we do this? And how is this useful? And how can we use it in definitions? And that's what's next. So we're going to take a look at what are called dependent and independent events. And conditional probability plays an important role in both of these definitions. So here we go. Let's look at a situation where you have an event. And so we're going to say our event is the card is a heart. So what is the probability of drawing a card that is a heart? And we're looking at it 2 different scenarios. Number 1, just straight up, all by itself with the full sample space, all 52 cards. What is the probability of getting a heart with all 52 cards? So if you take a look at that, the probability of getting a heart with all 52 cards, there are 13 hearts. And so that's 13 out of 52, 1 out of 4, 0.25, 25%. Then we're going to look at the case of getting a heart given that the card is red. So now we're going to apply this restricted sample space. And so instead of all 52 cards, we're going to restrict our sample space to just the red cards. So now instead of 52, we have 26 cards, 26 cards. So the probability is 13 out of 26, which is 1/2, which is 0.5, which is 50%. And what you notice is that these 2 probabilities are different. When you calculate the probability of getting a heart by itself with all 52 cards, and then you calculate the probability given the condition that it has to be a red card, you get different probabilities. And because these are different, we call them dependent, because it depends whether or not you apply the condition the card has to be red. If you apply it, the probability is 50%. If you don't apply the condition, the probability of getting a heart is 25%. Different probabilities mean the outcomes are dependent. It depends whether or not you apply the condition. Now let's take a look at independent events, and you can probably guess where we're going with this. Let's again take a look at 2 scenarios. So first, the card is a spade. If you calculate the probability that the card is a spade, straight up with all 52 cards, there are 13 spades. So that's 13 out of 52, which is 1 out of 4, 0.25, 25%. Done. And then we're going to apply the condition that the card has to be a jack. So if you take all 52 cards and restrict the sample space down to just the jacks, you have 4 jacks. That's your new restricted sample space. Of those 4, how many are spades? 1 is a spade. 1 of the 4 is a spade. So if you apply the condition, what is the probability of getting a spade given that the card has to be a jack? The probability is 1 out of 4, which is 0.25, which is 25%. These two probabilities are identical. And because they are identical, that means they are independent. That means it doesn't matter if you apply the condition that the card has to be a jack. Find the probability the card is a spade with a full deck, 25%. Find the probability the card is a spade given that it's got to be a jack, 25%. Same exact identical probabilities. So it's independent. It doesn't matter whether or not you apply the condition or not. They're both independent events. They're independent of each other. Doesn't matter. Apply the condition, don't apply the condition, you get the same probability for the event that we're looking for, which is the card is a spade. And so we go through a couple examples like this where we give you 2 situations. So here's the event, the sum is 7, and here's a condition. And you're going to find the probability of just the event by itself, and then the probability of the event given condition B. So given condition B means you're going to find a restricted sample space. You're going to compare those 2 probabilities. If they are different, then A and B are dependent. If they are identical, then A and B are independent. Identical means independent, II. Different means dependent, DD. Get it? So mnemonic devices to tattoo on your brain. So here's the probability of A all by itself. Here's the probability of A given B, and you get this. And you can see that these 2 probabilities are different. And so therefore, A and B are dependent. It matters whether or not you apply the condition because it changes the probability. Sometimes conditions change probabilities. Sometimes they do not. And when conditions change probabilities, when you get a different probability, that means that the 2 outcomes are dependent. If the condition does not change the probability and they remain identical, then they're independent.